So we're talking about screw threads today, and how to use the tables to design a tapped hole. In the old days when you were drawing by hand, you needed to know, until you had a lot of it memorized, you know, what the tap drill diameters were, what the minimum depth of thread, proper call out information is and it still is found in tables. You know, nowadays with CAD and especially three-dimensional modeling, it's pretty much information that you don't need to have at your fingertips or look up in a table. It's already there for you when you decide what size hole you want to put into the part. So the software does most of it for you. So let's look at the tables anyway. We're going to look up some values for unified metric threads, so we can find the pitch, the minor diameter, and the tap drill diameter. And usually, if you don't have information on hand that you need, you can assume that the minor diameter is about 75% of the major diameter. Mm-hmm. So if it's a 1/4-20 tapped hole or a 1/4-20 screw, the minor diameter should be roughly 75% of the major, which is a 1/4 inch. So you just multiply 0.25 by 0.75, and that'll give you the minor diameter, or an approximate minor diameter. So here's what a thread note looks like, unified. So that means it's inch. It is, well, let's go through it. So the 3/8 is the major diameter. The 24 is going to be threads per inch, because that's how we call them out. The UNF is the thread form and the series. So thread form is actually Unified National, and the series would be fine thread. The 3 stands for
class of fit.
Class of fit, right? Thread class. The B stands for
internal.
Right. If it were A, it would be external. So that position, at least, stands for external or internal. And then the lastly on that particular line, we're calling out whether or not it's left hand or right hand. And then finally, the line underneath is the thread depth, if it's not a through hole. If it were a through hole or tapped all the way through, then you would not need to call that out. If you had a through hole for the tap drill, but you only wanted to thread it part of the way, then you would have to call out the thread depth again, even though you've got a through hole. Does that ever happen? Probably. I'm not exactly sure what the situation might be where you would do that, but I suppose that you know, there's situations. I can't think of any off the top of my head, but if you can do it, then I'm sure somebody's done it already. So we break it down. This is what the breakdown looks like, you know, as a list. We don't need to go through all this stuff again, except for thread form, and I'd like to look at that, at least thread form and series, because the shape of the thread is Unified National core, you know, and then the series is coarse. So coarse is for general use. It's good because it's easy to cut, and generally for most applications, the strength of the thread is good enough. A fine thread, unified national fine, is used when you've got when you need more control over the strength of the tapped hole. A thread, a fine thread, is usually stronger than a coarse thread, but there's other issues that you run into when cutting fine threads. So they're not used really unless they have to be. And then the extra fine, unified national extra fine, is basically probably used on, like it says, for limited engagement opportunities like sheet metal, and also if the fastener is extremely small, then there's a pretty good chance that you may have an extra fine thread on that fastener. So again, this is something that's hardly used, but it is used in case of sheet metal when there's no opportunity to put some sort of backing nut on there. However, that type of situation, you can't expect there to be a whole lot of strength in that connection. So you use it sparingly.
One thing I was going to say, I noticed reading the book and looking at the slide earlier, they left out the NPT series, the National Pipe Thread.
Yeah, we don't cover.
Yeah, we don't cover it.
Right, we don't cover it. It's not. Again, this is just the basics in information on thread class. Now, we don't usually. I mean, I don't know where you would actually cover that as far as like a class situation. We don't talk about how what the difference is in tap drill diameters, or how deep you have to tap that hole in order to get the correct interference between the thread in the hole and the thread on the fitting that goes in it, because there is that situation. And if you over tap the hole, you can get a situation.
It'll be too loose. Yep, it'll be too loose. I know.
Right.
Done it. I've done it.
So,
I know.
Right. So there is that information out there, but it's not. I guess whoever put the class together initially decided, and I don't know that I never looked through the rest of the information that's available, because these aren't all the slides that come with the book and the instructional material.
Well, they didn't talk about it in the book.
Right. There may be some, they don't talk about it in the book, right?
Right. Do not. Yeah.
So I don't know if there's any extra information in the slides that weren't used in putting together these presentations. So, because I inherited these, so I never, not being a permanent member of the staff, I didn't really want to. I didn't want to modify the presentations too much.
Mm-hmm.
Knowing that next semester or the following, I might not be teaching it. I could be teaching something else or not teaching at all, as the case may be. So I didn't want to modify them too much. So there may be some slide information on there. I'd have to look and see. But yeah, I think it's just they're just not. There's not enough time to go through everything related to this. We're not. There's a lot about threading and fastening that we're not covering. So anyway, so here's the exercise for writing a thread note for number 10, fine thread. So what they want you to do is they want you to look up Appendix B and find this page in the book, which I don't know that you really have to do, but you can see the number 10 is is highlighted here. So when you look at, when you're looking up a thread to find out this information, you basically look it up as the threaded hole or the
True diameter.
yeah, it would be called out. You know what I mean? So if you want a number 10, you look up a number 10, and you look at the major diameter, which is 0.190. For I don't like the way this is spelled. I don't know if it bothers anybody else, but let's see what the how they call out. See, here it's correct. This is the way coarse should be spelled,
Mm-hmm.
right? Because that's what it means, rough.
Right.
More, right? It references roughness. When you look at this word, that is a
That's what we have now, of course.
That's what right, but it's also, I mean, it's a system of instruction and direction to get you through a certain point. When you drive on a race course,
Mm-hmm.
it's the same thing, right? It's a system of
Yeah.
direction.
That's a misspelling on the slide, because in the book it's actually spelled the correct way.
Yeah. So anyway,
I just looked.
Yeah, that's an aside. I'm just, of course.
I don't blame you. I get bent like that too.
That stuff bothers me in, like on Facebook, and I read a lot of articles with grammatical errors and misspellings, and it bugs me. Anyway, so we find the line for number 10, and then we're looking at the information for fine thread. So we look at the threads per inch. The fine thread has 32 instead of 24. Right. But also the tap drill diameter, I mean, it's different than what it would be for a coarse thread. So you can't necessarily just say, hey, I'm going to, if you know what this is off the top of your head for a coarse thread, you can't use that necessarily for a fine thread. I mean, you could, but you'd have difficult tapping it, and you might just, gall the threads or
break the tap.
Yeah, break the tap or misform them. I mean, is there a reason? Do you know why there's a difference in the diameter? Or do you wonder why it is? I don't know if I know the right reason, but there's there is some reasoning, I'm sure. There's some solid engineering back.
Because the fine thread is exactly that, fine thread. If the way it cuts the thread is slightly different, because you have to cut it so fine. You have to leave room in order there for junk to fall out while you're forming the thread.
Yeah.
And it doesn't. And the thread, I think I read in a book that the fine thread doesn't quite cut as deep as the coarse thread either, and that's probably why you're controlling it with that bigger size drill. Because if you look, that drill is about 10 thousandths bigger than the other.
Yeah, it's 10 thousandths bigger. Well, might give or take half of the,
Right.
5 10,000ths. But the other reason I think is the fact that if you were to use the same diameter drill as you do for the coarse thread, when you cut those fine threads, you're cutting so many more threads. Mm-hmm. Like you said, you're creating more, chips and what have you. But you're also, because you're cutting away more material, I think you have a greater opportunity to misform a thread, to have the threads not cut as cleanly as they would if you increase that minor diameter a little bit. So you're moving a lot. Excuse me. You're moving a lot more material. You're cutting away a lot more material with every turn. Mm-hmm. Takes an extra bunch of turns in order to do 1 inch of thread than for a coarse thread. So yeah, I think you're on the right track with that. So yeah, so you find the information and then you have to assemble the call out. So again, SolidWorks, or any CAD program, at least a 3D that's got any substance to it, is going to do that. But and imagine the 2Ds. But when I think about like AutoCAD of old, there was never an automatic call out for a tap hole. You still had to do the call out manually on the thread node. So you still had to organize the information, and this is what it would look like, except that this is normally everybody in the country would do number 10-32
Right.
UNF.
Right.
But the standard wants, the standard prefers that you use the decimal call out or decimal equivalent. So, when you look back at the chart, all the numbers are, they have a call out. So a number 5 would be, you call out as a 125 by 40 or 44 or whatever the case may be, whether it's coarse or fine. And again, I think they're just trying to make it so that there's no guesswork for somebody that's not familiar with it as to what we're looking at. So we start out with the major diameter, threads per inch, the thread form and series, and then if everything else is basically the default, which is class 2 and right-hand thread, then you don't need to include that information. So this stuff is optional. You don't have to necessarily include the class, whether it's external or internal, and whether it's right hand or left hand. I mean, usually you got to figure if you're putting a leader on a bolt or a shaft like this, it's external thread, right? If it's threaded internally, you're going to show it. You're going to show an end view with an end view with a hole, and you're going to call out the thread that way, and it's going to be obvious that it's an internal thread. So, and if it's not left hand, you don't need to show right hand. So that's what a unified thread callout would look like. So let's look at metric notes now. A little bit different, as you can see. The M indicates that it's metric form. The 6, or the second position there, calls out the major diameter, which of course is going to be millimeters. You don't need to show a diameter symbol in this call out, just like you didn't need to show it in the unified. Position 3 is the pitch, right, which is different from the unified. The unified talks about threads per inch, right? So in order to determine what the pitch is, you have to take the number of threads per inch and divide that into 1. So you have to take 1 divided by the number of threads per inch to determine what the distance is between crests on that thread form, which is what the pitch is. The metric callout gives you the pitch automatically. It says, hey, we don't care how many threads per, centimeter or decimeter or whatever. We don't care about that. We just care about what the distance is between crests, what the pitch is, because ultimately, I mean, that determines a number of things. You might use it in calculating the strength of the connection. It tells you whether or not it's coarse or fine thread. And it works differently. It works the opposite of what a unified looks like. And we'll talk about that, I think, a little later on, or maybe I'll mention it right now, is the fact that as the threads get finer, the pitch number goes down, right? So as the pitches get, as the crests get closer together, that distance decreases. So if this were a fine thread, an M6 fine thread, it might be 6 by 1 point, not 1.25, but like 0.8 or 0.8 or 0.7 or 6 or whatever it is. I don't honestly know what it is because it's in the table. I don't remember what it is. But if this happens to be a fine thread, and then the coarse thread might be M6 by 1.25, because that distance then between the crests is going to increase. So that confuses things a little bit, but you'll get the hang of it when you see the tables. Number 4 is the tolerance class. So they don't use class of fit, and they don't use right hand, left hand. They use tolerance class. And then it's broken down here a little bit later. But they do, of course, use, indicate whether it's right or left hand thread. Again, if it's right hand thread, you don't usually have to call that out at all. Not sure, the tolerance class call out is a default that has to be there. So anyway, we look at that. Now we're looking at two different tolerances here. We're looking at the pitch diameter tolerance. So they control that pitch diameter, and that makes a more uniform thread. And obviously, the tighter you control that, probably the stronger the connection is going to be. And the same thing with the crest tolerance versus, over the minor diameter. That is it's something that helps keep the formation of the profile of the thread a little more accurate. There's standards to use that you don't call. I mean, again, not normally called out unless you're specifically trying to hold tighter tolerances on that thread form. Just like in unified, you don't necessarily call out the class, and whether it's external or internal, because if it's the default, which is class 2, you don't need to call it out. The only time you need to call out the class is if you don't care about the accuracy, and it can be a loose fit, or on the other end of the spectrum, you want it to be a tight fit, so that there's less clearance between the mating threads. And then again, the last line, the second line, is the thread depth if it's not a through hole. If it does happen to be a through hole and it's tapped all the way through, then again, you should not need to call out the depth of thread. So again, we can go through some of this stuff, but let's look at tolerance class. Again, it just describes the looseness or tightness of the fit between the internal and external threads, kind of like what I had said, previously, and just like the class in unified column. So we're trying to find the different components of the following. I think this thing actually shows up twice in the. I don't know if this is the slide or the presentation that it might come up twice. We'll see. So we want to identify the different components of the following metric thread node. It's an M10 by 1.5. It's a 4H6H tolerance class right-hand thread, right? So I just pretty much gave it away. M stands for metric form. We already covered all this. The 10 is the major diameter. It's a 10 millimeter major diameter.
And the pitch.
Pardon me?
The pitch. 1.5 is the pitch.
Yep, the pitch. Next one is?
It's internal thread.
No, we haven't done the 4/8, 6/8 is what?
It's the class of fit.
There you go. Tolerance class.
Right.
Tolerance class. Class of fit is the verbiage for unified.
Right.
But I won't dock you for that, Bob.
Thanks.
Yeah, internal or external.
Okay, so the external probably has the small letters and the internal has the larger letters, the capital letters. Is there a way to differentiate that in the?
Let's go back and look at.
So like this one's got the capital H's in it for the class of fit,
Yeah,
the tolerance class.
yeah.
When we looked at the other one that had the external threads, it has small, the lowercase h's.
Well, let's find out.
Yeah.
And we know that RH is right here.
Right. Exactly.
So, I don't know if they're going to talk about that today.
Yeah, they may not. And I don't remember reading it in the book either, where it actually told you that. And it might be just you have to look at the chart.
Yeah, and I'll be honest with you, off the top of my head, I can't recall if that's the case or not. But because again, you know, if you're pointing to a shaft, a threaded shaft, it's you kind of, you know, it's pretty obvious it's an external thread. And if
Right.
you put it into a hole, it's an internal thread. So I never really pay attention to it, even when I teach the class. So let's go through this, and then I'll take a look at it, and I'll update you guys on whether or not that's the case.
Okay.
So for a 16, a diameter 16 internal metric thread, what are the available pitches, and what's the tap drill diameter? So now you have to, in order to find that information, you have to go to the table again.
Right.
So when you look at the tables, this should be Appendix B.
Yes, it's like on page 8, B3 in the book.
Yeah, I'm looking at B3 right now.
Mm-hmm.
So if you look at B3 in the book and you find an M16, and you look across M16, you'll see that we're basically, for coarse and fine thread, we're showing basically two different thread pitches, right? Either
Right.
2 millimeter or 1.5.
Yep.
For coarse or fine.
Right. And a 14
So
or a 14 and a half for the tap drill.
Yeah. So, oh, yeah, we need that too, right?
Yep.
14 or 14.5 for the tap.
Yep.
So for the pitches can be either 2 or 1.5, and the tap drill is either going to be 14 or 14.5. So now we want to write the thread note for a 16 millimeter diameter coarse thread. So the first thing we're going to write in there is going to be
the
M
16 probably by 2.
So yeah, we look at that chart and we look at the M16 for coarse thread, and it's going to be M16 by 2. It tells you exactly what it is right there in the chart.
Yep.
And so the other information would be, now here, see, these are capitals.
Yep, they are.
Right. And what you were saying before was it doesn't tell us whether or not, it says it's external.
Right.
So,
that's
right.
Smaller. Right.
Right. So that may be the case there, that the lowercase alpha characters on the tolerance class indicate that it's an external thread. Well, let's see if that pattern holds true. I don't know if we'll get another chance here. I don't think we will. Because I think this is going to be the last slide for the presentation right here. Again, this information is optional as long as we know that we're just going with the default tolerance class, and that it's it's defaulting to a right-hand thread. Don't need to show that information.
Right.
So the call out's pretty easy, right? And the only thing you'd add, if this were not tapped all the way through, would be the depth of the thread on a line underneath. And again, working with SolidWorks, it's as long as you use the right command, you won't have any problem with this. So that's the end of what we're talking about for thread call out and how to call them out here. Basically it's just a question of using the tables and using some deductive reasoning as to how it should be, how everything should be arranged in the call out. Again, using SolidWorks is going to be pretty, it's going to be pretty straightforward if you use the right command. So we're introducing a new drawing project, the P150, and I want you to look at that. But first, I want to go back to the one that we were using the other day, Monday, which was this guy right here. A couple things I wanted to show you was remember when I was trying to modify the text and increase the size of those arrows or the A's over the arrows, and I selected this guy and said, hey, I don't want to use the document font. I want to change my font to something a little bigger so it can be seen better. And I want to go to points. I could just go ahead and double it. I could do this. I could double up the size. Let's call it, say, 0.25. And it's going to ask me if I want to change this one as well. And I'll say, yeah, okay. That one updated. You see how it got bigger?
Yep.
These guys didn't for some reason. I don't know why it doesn't update it automatically, but it's one of those situations where if you don't see a change after making, thinking you're making a change, is to go up to this icon right here, the rebuild icon, the stoplight, and click that. And when I do that, see that they update it.
Yep.
Yeah, they update it. I'm not sure why why these do and this one doesn't, but sometimes that's what you have to do. And so remember, I put a tapped hole in this guy, and it's tapped all the way through. If I just go with a smart dimension call out on this guy, I might get a call out like this. Sometimes it works, sometimes it doesn't. 1/4 UNC. So that's not so bad, right? But sometimes it doesn't work like you expect it to work. The best thing to use for the tapped holes again is this hole call out, like we would use on the counter board. Again, if I just use a smart dimension on the counter board, what am I going to get? I'm just going to get that diameter, right?
Right.
And I can't, for whatever reason, select that outer edge. But if I go ahead and use the hole call out, even though now I can select the outer edge for whatever reason, and it gives me all that information, right?
Mm-hmm.
All the correct counter bore information. Well, if I go ahead and use it on this tapped hole, you see the difference in the call out. It gives me the tap drill diameter, and then it gives me also the tap information.
Right.
And it added through all to it, which, according to the ANSI standard, is not. I don't know if that's kosher or not, because it's some, it's verbiage. But like I said, some of this verbiage is designed to be universal, like THRU. Obviously not the correct spelling of through. So it's becoming kind of like a symbol.
Mm-hmm.
Okay, so here's the deal with the two callouts now. I'm going to modify that tab total. And I'm going to say, hey, I don't want you to be a through all hole. I want you to be a blind hole. And this information isn't correct because I don't know what, I'm not sure why it's defaulted or to user modified. When these things are yellow like this, that means they were user modified. So I want to say, hey, it says it should be, the thread depth should be 2 times the diameter. Well, we know the diameter is 1/4 inch, but I have less than half a diameter for thread depth, which isn't much. So if I hit restore defaults, now it gives me a blind hole of 650. And I know that this is 3/4 of an inch. And now it gives me a thread depth of 1/2 an inch, which I like. So I'm going to say, okay, I'm going to go with that guy. And I'm going to control tab over back to my drawing. And you see what it did?
It changed it, yep.
Yeah, it updated my information. This guy didn't change, did it?
Right.
Right? And now it's a blind hole. So if I were to use this call out, then like this, if the machinist isn't paying attention, he might go ahead and just say, oh, there's no depth information here, so it must be a through all hole. So he goes ahead and makes it a through all hole, and then I come back and say, hey, what happened? The part's not right. And he says, well, this is what it said, and that's, so whose fault is it? My fault. Right. So you want to make sure that you use this whole call out tool for tapped holes also. That way, if they get modified in the future, the call out will update automatically. That's pretty much it for this guy. You want to take a look at the project. Let's take a look at the project. Let me go back to, I've got the project here. Let's look at the homework that's assigned today also. This 8687 practice. I want to make sure that everybody understands certain things here. Because there's confusion for some folks as to how many parts we're actually supposed to do. Like on the, for the fits, the limits and fits section, we know like the first problem we had like 8, you had A and B to do, and there were 4 fits under each one. And so that meant a total of 8, and there were 8 tables to fill in. And I had a lot of homework come in that just had 2 tables filled in, 1 for A and 1 for B. And so I had to go back and explain things. So I'm trying to be preemptive here. So it says for 831, parts A and D only, 82 for problem 82, A and F only, and problem 83, A and C only, and blah, blah, blah. So if we look at the online version, I should have guessed that. Let's see if it brings me. There we go. At least I didn't have to do all that. So here's problem 81, 82, all on the same page. And what did it say to do?
Let's do A and B for 821.
Yeah, A and B, right?
Right.
So this is more simple than the limits and fits one was. So you're just going to fill in 2 out of the 3 tables, I guess. But but you got to write the thread note, right? You have to write the thread note. You have to call out the minor diameter and the pitch. So write the thread notes for the following external threads. Also, what are the minor diameter and the pitch? Thread class is 2, so we don't necessarily have to call that out. It doesn't say that any one of them is left hand, right? So we don't have to worry about that. But like this one says, this one's asking for tap drill size or diameter and pitch, and it's telling you that the thread class is 3. So when you write out the thread note, you're going to have to add that information into the thread note for the 2 that you do for 8.2. I don't know what was the other one, 8.3?
Yeah, 3.
Yeah, 8.3. So again, the thread note and the major diameter for the 2 that you do for 8.3, and then 8.5. Was it just 8.5?
Yeah.
Yeah. So anyway, just make sure everybody, because this is the video I'm going to post, that you read the instructions and go back and review the PowerPoint in order to make sure, if you need the information or to review the information on how to write the thread notes. This, by the way, is the online version of the book that is available to everybody in the class until May 25th. I don't know if it does you any good or not, other than the fact that if you want to, you can't download the pages. The only thing that you could do if you wanted to, for some reason, not do this in the book, is you could do a screen capture. Wherever mine is, I don't see it on my, there we go. I could do a screen capture with the snipping tool and then save and print this guy. So I could do that. But there's no way to download the pages. But if that's an option for you, by all means, sign up and find the book. It takes a little bit of navigation in their website to find the book. But I think on the home page, all you have to do is type in the name of the book, and it'll bring you to another page that lists all of the variations. There's a couple of older publications with the same title by the same author. And there's some other books in there that start out, that are for SolidWorks 2019 or AutoCAD or whatever, but they have the same basic title. So you got to look to find it. And then once you ask to download it, it'll have you fill out a couple of lines of information as to what your school address is, email address, and that kind of thing, and then it verifies it all and gives you access to the book. Again, don't know how much help it's going to be unless you didn't have the book, or you don't want to write in the book for whatever reason. So, but it helps me out in terms of putting the stuff on the screen so that you can see it. So let's get back to SolidWorks. And I want to open, no, let's say no. And I'm going to say no. And I don't have that open. The newest project, the P150. Let's look at the instructions real quick and see what it asks us to do. It says use the 1A checklist to create revision A. Be sure to dimension all features, not just the ones described below. Consider possible applications of GD and T. Feel free to practice other SolidWorks features such as as needed, including supplemental views, revision table and balloons, tolerances, datum features, so on and so forth. So there's some leeway in this drawing project as to what you're going to put on here and how you're going to arrange everything. It does tell you to, that you got to do this in the title block, that the material is aluminum. It says create proper thread notes per chapter 8, add surface finish and weld note as directed in class, which we haven't done yet. Print Rev A and exchange drawings with a classmate for feedback. We can't do that. Update to revision B and incorporate any checker feedback. Again, you won't have any checker feedback, so unless you partner with somebody online and exchange files and have them take a look at it, there is that possibility. But I don't know how, not knowing everyone's school, well, maybe you can get it. When I send out a blanket email to everybody in both sections, if you were to open that email and try to check the to section of it, could you find everybody's email address? I wonder. I never thought about that. So that you could, realistically communicate with somebody if you needed to or wanted to. But I don't expect that. So I just expect you to try to, on your own, think about, adding some of this stuff. What I would do if I had left that stuff open, what I would do with my drawing is let me pick. Let me pick this guy. So what I would do with surface finishes, I would say, for example, we haven't looked at surface finish yet, or how to apply it, but it's pretty much like everything else. If I were going to control a hole and put a datum, put a geometric tolerance on this hole, for example, I start with the symbol, right, and go to position and say I want it to be diameter 0.005. Let's just call it 0.05 from A B and C. Sorry, I had an issue with my right, and then I've got my call out.
Mm-hmm.
Okay, so to do a surface finish, it's kind of the same thing, except you don't get the dialog box out here. You just get the property manager, and all we're trying to do is put a finish, a symbol like this on a surface. But we have to call out. We should be calling out some type of finish for this surface. So, say we haven't really talked about surface finish yet, but I think I did mention previously that it's grades. There's different grades of finish. And as the numbers go down, the finish gets finer. We talked about the cost of producing a part when you've got. If I have a finish of 16 or 8 on this thing, then I know we're going to be honing and maybe lapping. If it's a 32, then I'm probably going to grind. 64 might be I might be able to get that with an end mill or some type of milling tool, kind of like right on the edge of one or the other. 125 to 250 are definitely going to be machined, or there could be stock surface finish. you don't usually want to leave it blank. And a general finish, if it's going to be machined at all, or just basically machined, we would make it a 125. And this is where we would put it, in this box right here, 125. And then when I look at the surface, the finish symbol, this is what it looks like now. It has the 125 in it. And if I attach it here, that's where it's going to stay. If I go to attach it on this edge here, for example, it's going to turn. It might not turn the way I want it to, but it should turn. And if I attach it, say, on a bottom finish, again, it may or may not turn. On an angle like that, it aligns itself with the finish, but maybe not in the direction you want it to be. So, so the thing to do is to place them and then modify them afterwards, and just say, hey, I want you to be this way. So I picked down here in the property manager a couple of different options. But this one says, hey, I want it to be perpendicular in a reverse way, other than the default. Notice that, that the section hatch there kind of modified itself so that it didn't cross over this, but now I've got a hole there. Let's see what happens if I hit rebuild. Does it change? No, it doesn't change. So I'd be willing to bet that if I saved this and then reopened it, that it probably would update. We'll find out at the end here. So again, this guy, I want to say, hey, I want to reverse you. This guy, I want to reverse you. And you, I'm going to reverse also. I can, if I pull on it, I can't take it off that surface, but if I can drag it along the surface, I can put it out on a leader, if I want, or an extension line. Now notice this one is not, regardless of which way I go, I can't get a gap, and that's probably because I put it on here. And if you think about it, it's probably looking at this as this being a separate line, this being a separate line, so on and so forth. If I were to redo this guy and say, hey, I want to put you on, I'm going to go right on the end here, and I'm not going to put up. And now if I drag it off there, you see it's got a gap. So that's the situation. Sometimes you got to look at that and say, hey, how do I want this to be? Same thing here. This is probably, it looked at this section as a separate line, and this is one. So there's no gap here, but there's a gap if I drag it that way. This one I'm going to just leave where it's at. This guy I could drag off if I wanted, but you don't have to, unless it's in the way of something. So that's it for surface finish. A weld call out is the same thing. If I want to put a weld symbol in, this time I get a dialog box. And we talked about weld symbols prior to this, about how they're arranged, whether or not they're, depending on which arrow, which side of the line the symbol's on. Then determines whether it's arrow side or the opposite side. So if I pick my symbol, we start again, just because I want to make sure I'm picking the right one for everybody, because I'm going to put it right in this corner right here. And again, it kind of works like the geo tolerance. It starts to want to put to put a leader on right away, and I don't really want to do that. I'm going to just go ahead and say, hey, here's my weld symbol. This is a fillet weld. That's what we're going to use probably 99% of the time. So we're going to say, hey, let's put a fillet weld in. And let's make it a quarter a 1/4 inch leg for effective throat. So leg is what it is. So we'll just say a 1/4 inch. Now there's my symbol. If I want to put it right in this area right here, I can attach it, say okay, and I'm done. And I'm saying it's on the arrow side, so that's because I have the symbol down here. If I wanted it here, which would be kind of difficult. I mean, they could do it because in reality, you'd be welding it. If I wanted to, you know, this isn't necessarily the best place to put this either. But I could, because it doesn't attach itself the same way. I could move it from one view to the other. I can also modify it to say, hey, I want this to be, I have to double click it, an all around weld. And it adds this circle right here, and that indicates it's all around. So now what I've done is taken it from a 1/4 inch fillet weld that would just be welded on this edge right here, or this junction between these two parts. Now I'm saying, hey, I want it all the way around, as far as you can get it, which would be right to here, because we got that hole in there. So I could say, yeah, I want it all welded all the way around. That's basically all there is to it. And you've got this video now, or you will have, to look at to see how to do all this stuff. That's it. Any questions? Make sure that you're modifying your, if you do cut a section in this thing, I don't think you're going to have to. You want to see the part. The part looks like, I already have some of ours open. I don't want to open another one.
No, but you're right. It did fix itself up. Did you see that? The hashing on that?
Yeah. See, once I yeah, I didn't close it out, but once I minimized it and brought it back, it updated. So it's kind of cool, you know. It's kind of cool that it. Now I see it's not doing it when I placed it. So let's see what happens when I minimize it and then maximize it again. Yeah. So you have to take that with a grain of salt. The other thing is, if you don't want to flip them around like that, you can leave them like they were. Like this one, for example, I can flip him back this way and just put him out on a leader like this. And that's going to basically say the same thing. It doesn't have to be flipped over unless you can't put it on a leader to get it out there. But this is acceptable as well as you know, flipping the symbol over. That still says, hey, we want a 125 finish on this surface. And now look, it updated. That's it, right? It just, I don't know why it's taken a while, but yeah, you can do this too. You don't necessarily have to flip them unless you can't get a leader out there. So either way is fine, as long as we're not, we don't have this situation like for this guy. That wouldn't be right, because now you've got, it's kind of like putting a dimension inside a part. That's a no-no. This is a no-no. So you want to definitely have that guy flipped out there. But getting back to what I was trying to do to begin with, which was open that other part. Just so you can see what the part looks like. That's the part.
Mhm.
So that might take a little bit of work. And I'll tell you what else you're going to be up against is that these aren't normal tapped holes. So you're going to have to look at sizes and see whether or not they're actually correct. And figure out what you're trying to call out, what they're trying to call out here. Because these holes are actually put in with, you see, it's just it's a cut extrude with a cosmetic thread.
Mhm.
So you're going to have to kind of figure out what size it is by looking at the drawing. But once you put the part into a drawing, let's see, let's make a drawing from this part. We just need one view, so I'm just going to use a basic A size. I'll take the top view. So look at that. When I bring it in, it tells me that there's a note attached to that cosmetic thread. But it's really not the correct note. And they're just leaders. You see how this is not on center, not pointing to the center of that hole. So it's not attached to it like a normal call out would be. And I don't think you can use the hole call out on this. You can use it on this, but it's just going to give you the diameter. It's not, you won't be able to grab the hidden lines. I can't grab that hidden line and say, what is that? Can I measure it, or can I put a regular smart dimension on it? Yeah. So even that doesn't tell me exactly what I'm looking at here, does it?
Mm.
But my units aren't correct for this drawing. So let me update my units. So now it says, hey, that's a 10. So now at least I know that it's 10 millimeters, and which is what this said here. So I've got to call out this thing correctly. So basically what I would say is you take these, the notes that appear on this drawing, on this part, when you put it into a drawing and modify them, create your own call out. But you can start with these if you want. And if you want to figure out the depth, these other ones are through holes, but if you want to figure out the depth, when you bring in a view of this guy, I'm going to project the view down here. And I'm going to say, hey, I want this to be, to show the hidden lines. Well, there isn't much depth there, but it is there. So you might have to do some measuring to find out how deep that threaded hole really is, how deep this hole is, right? So because you definitely want to call that out. And then I don't know where these call outs came from actually, but that looks pretty good to me. I'm 12 by 1.75, and it says 2x on it, but it's not in the right view. So you're going to have to play with this a little bit to get the information correct. Even if you just go ahead and put a dimension on from here to here, if you want to use that as the depth of the thread, because you also got a countersink to call out here, and you're going to need, what are you going to need on this thing in order to dimension this properly? Does anybody know? Do either of you know?
An auxiliary view?
Yeah, you're going to need an auxiliary view. And auxiliary views are pretty easy to do. Again, view layout, auxiliary view, just pick the edge that you want to go from. I think I showed you guys this already. And then there it is.
Right.
And so, because it's, I'm in a confined space here, so everything's going to be on top of each other. But if you're using a C size, you should have plenty of room. But I could, because the view's called out, I could break the alignment and move this guy down, somewhere else. Change this guy or move this a little bit, maybe, so it's out of the way. Can't separate it because it's not the right. It's not the right. I'm not in the right dimension standard. So, in any event, yeah, that's what you're going to have to do, and you probably won't have to break the alignment on it. But in order to be able to dimension this stuff, you're going to need that, and then you're going to need another right side view of the part. So I'm giving away, as much as I'd like to give away on this, but I don't want anybody to struggle. So that's it. That's what I give you so far for this particular project. When's it due? Due April 29th, but you got until May 6th. So, because April 29th is like 2 days away from the drop dead date for every other assignment. So I got to give you some time, right? Some extra time. So I gave you the same amount of time as you have to get the quizzes done. All right.
Okay.
That's it. Everybody have a great weekend, and I will talk to you on Monday. If not before.
Okay, Frank. You have a good one too.
Thanks.
Thank you.
Thank you.
Bye-bye.
Bye.